Good morning, everybody. Except that there doesn't look like there is anybody right now. And I hope this is all working. I've changed a couple of things around on my computer and I just had to set OBS up again. So I don't even know if I'm streaming. Looks like I am. I'll assume that there are people out there. So, oh yes, unexpected maker. Hey Sion. So I've got one person with me this fine Sunday morning. On previous live streams, I worked down through my Eagle projects and made it as far as the end of the letter B. So, oh, hey Rob. Yep, we've got people coming on now. So, the next project in the list is actually one that is really important to me, and it's a good one to be starting with today. So, it's the chair breakout project, which is the electric wheelchair control system breakout that I've been working on for quite a while now with Nick Fryer. And so if we have a look down in my Eagle list, I've got a project here. Next in the list alphabetically is actually CB Mini. I'm going to skip over that and come back to it in just a second. CB Mini is the newest version of the control system breakout. And it's like basically version 3. So the chair breakout is the earliest version, the earlier one. So I'm going to start with that and explain some of the background of this project and how this design came about and why we ended up with where we are now. So in the chair breakout project, I'll jump over to that. And what is going? Oh, yeah. Yes. And switch to the desktop. So this is the schematic for. Well, this was version 2 of the breakout for the wheelchair control system. Before I actually get into this, I'm going to show you a little bit about what this is actually connecting to, because this design is done in the context of an existing system that we're wanting to integrate with, and that presents challenges of its own. A lot of the time when you work on particularly hobby projects, what you're doing is designing a board in isolation. So you are making something that works, like you apply power to it and it does something. It might connect to sensors or actuators that you have set up, but there often isn't much of an external system that you need to integrate with. So what I'm going to do is switch over to the desktop, like the top-down camera, and show you a little bit about what we're linking to. Now, so to give you context, Nick, who I have been working with on this project, has a genetic disease called Duchenne muscular dystrophy. What that means is that it's a degenerative disease, and there is no cure at this point. It's a matter of doing as much as possible to delay the effects of it. Is really all that can be done. And over time, he loses the ability to control the muscles in his body. So when he was young, he could, run and jump and he was fine. And then over the course of his life, and he's now 40 years old, he has progressively lost the ability to control the muscles in his body, which means that they have atrophied, and so he has almost no ability to move or to control things. So he uses an electric wheelchair to get around, and he can move his fingertips in order to do things like move a mouse if the mouse is in a very high speed mode, because the amount of movement is very small and the amount of force that he can apply is very low. So for example, if he wanted to control a computer game with a game controller, he doesn't have the ability to push the joysticks because they require too much force to move. with a typical game controller, they're designed for for people with typical levels of strength, and usually getting rather excited in the game. Like you grab a game controller and you're bashing it around and squeezing it. So game controllers are usually extremely robust, and they require a fair bit of force to move. And the same goes for things like the remote controls for flying a drone, or remote control plane, or anything like that. So a lot of the things that that most people can do without thinking twice about, he's not able to do. Now, on his wheelchair, he has a control system which uses a thing called a mini joystick. And the mini joystick, which you can see in a top-down view here, and I'll give you a detailed view in a moment, is designed specifically to be usable by people with very reduced strength and very small movement of their fingers. So this particular joystick, I'll slide on over to it, is designed to integrate with the control system of his wheelchair. And we have one here which is just mounted on a wooden block for testing, because this is one that I've been using while I've been setting up this circuit, and I just wanted a way to conveniently put it down on the bench, and then it just sits there and I can use it to test that the signals that I'm getting are what I expect. So the joystick itself in here uses a Hall effect sensor, and there is a very light spring. So if you look, you're looking side on now, and you can see this little cork cover over the top. You can get covers in different shapes depending on the particular needs of the user. So if I push this, that is full scale deflection. So that's the center point. This is full scale deflection to the right, center point, full scale deflection to the left. And the amount of force that is required to do this is tiny. It's around 12 grams, I think, of pressure. And yes, I know grams is a mass, not a force, but that's just how it's reported. It takes around 12 grams of force to deflect the joystick full scale, and it's extremely high resolution. So it only takes a tiny movement to change the output, and it allows control of things like electric wheelchairs for people whose total movement is only a few millimeters of their fingertips and with a very small amount of force. Now, different people who use different wheelchairs, or they might have different medical issues to deal with, need different types of control systems. So in the case of Nick and his identical twin Chris, they use these things, the mini joysticks, and that's ideal for their needs because it has that high resolution, it's got very low force, and they use these to control their wheelchairs. No problem, they can drive them around like champions. And for other people, they might have different restrictions. For example, it's fairly common to use either foot controls for someone that doesn't have enough control over their hands. So there will be a device on the wheelchair that allows basically like a foot control steering, and also things like sip and puff interface, chin. So these same joysticks can be mounted, so instead of using it with your finger, you can use your chin to move it. And so the wheelchairs themselves are designed to take a variety of different inputs based on whatever is appropriate for the user. And so what we wanted to do was give Nick and Chris a way to use this sort of control system, which is highly optimized for their use, and then use it for other things, not just for controlling the wheelchair. So and this is all normally permanently attached to the chair. So what you see here is the joystick, which is normally mounted on the frame of the chair, and then that has a cable that goes down to this little device, and this is an interface. Well, basically this is a driver. So inside the joystick itself, it's got the Hall effect sensors and all the mechanical part of it, but there's no electronics. the actual sensing is all done inside this little box, which provides an output that looks like a serial connection, but it's not. And this little box is actually quite sophisticated. It does processing of the signal from the Hall effect sensors, and it then sends signals back to that connector, which goes into the wheelchair control system, and the wheelchair control system can then use that to go forwards, backwards. So basically, it's speed and direction, X and Y axis outputs. So it's a 2-axis output from the joystick. And what we wanted to do was find a way to take the signal, basically break into the process. The wheelchair has this existing system with the controller, which is the brains of the chair, and it's got the input coming in from the mini joystick. So we wanted to basically snoop on the control signals so that we could then send that off somewhere else and use that control for a totally different purpose. So the first thing we had to do was figure out how this was talking to the wheelchair controller. And one of the things about most assistive technology is that there is almost no documentation for it. It's, well, none that's publicly available anyway. Usually it's very tied up in NDAs, and the companies that make this sort of stuff are really protective of their IP. They don't want any competition, basically because there is so much money in this. So to give you some context, a modern electric wheelchair, if you go out and get one set up, will easily cost north of 40,000 Australian dollars. And they obviously need to be customized. It's not, you don't just go and say, I want that. It's a process that can take months, where you go to a consultant and they get the chassis that's appropriate for your needs, and then the seat that's appropriate, and control systems and accessories. And the chairs themselves are incredibly sophisticated. So the first thing that we faced was that it's very hard to find information about any of these systems. So we obviously started with a whole bunch of Googling, and we found a little bit of information. There have been some people that have put work into reverse engineering them, and there's a great site called wheelchairdriver.com, I think it is, which has got a really big forum and lots of people that do wheelchair hacking. So we found some basic information, and it turns out that the output that comes from this is a couple of analog outputs and a reference voltage. And it's not as straightforward as you would think. So the way it works is like this. I'll see if I can draw a diagram for you. What's the best way to do this? Hopefully you'll be able to see it if I stick it on a piece of paper like this. So the box itself has, okay, we'll look at it from a voltage point of view. So we have the control box, and we have ground coming into it, and ground reference. So then we have a voltage input, which is nominally 12 volts, but it's a little bit fiddly. It needs to be somewhere just above 12 volts, but not too much above it. So like 12.5 volts. And that power comes from the wheelchair controller. So the wheelchair controller supplies power, like ground and 12-ish volts coming in. So we'll say 12 volts coming in here. And then on the output, what this interface gives is 3 connections. So one of them is X, one of them is Y, which seems reasonable enough, and the other is ref. Now this is where it tripped us up a little bit to start with, and the way the wheelchair controller actually reads from this is a little bit strange. What it does is take the reference voltage, which is usually half of the input voltage. So say we've got 12 volts coming in. What will be coming out on ref will be 6 volts. So I'm just using round numbers here to make it easier. And then if the joystick is in the center position, so X and Y are both centered, you will get a deviation from the reference voltage based on how much it's deviating in its position. So if, for example, you had the x-axis centered, so it's just sitting in the middle, it would come out as 6 volts. And then the y-axis, say you pushed it forward because you want to have you want forward motion, it actually goes down because the x and y-axis directions, the positive and negative signs are reversed to make it even more confusing. So if you push the joystick forward, so y-axis forward, it means you want to go faster. What it does is decrease the voltage on that output, and you might get, say, 4 volts coming out of the y-axis because it's pushed forward, so voltage is decreased relative to the reference voltage. But the thing is that the reference voltage can also change. Now, the reference voltage in testing, what we found is that it's usually approximately half of the supply voltage. So if we give it 12 volts, we'll get 6 volts out on the reference. If we give it 12.5 volts, we'll get 6.25 volts out on the reference. And if the input voltage changes, which it can do with things like varying battery conditions, etc., the reference voltage will change, and then the X and Y voltages will change as well. You might have a reference voltage, or you might have an X value that when you start working with it is coming out at 6 volts. And then time goes on, and now you are getting 5.9 volts coming out of it because the battery voltage has changed, but the joystick hasn't actually moved. So if you are trying to measure just the value coming out of the joystick, you can zero it initially, but then over time it'll start to drift, and then the joystick position will start to drift in your software because it thinks, hey, we're getting a different value now, and it's moving. Alright, so I've probably totally confused you now, but what this means is that what we really care about is not the value that comes out of the X or the Y axis. What we care about is the difference between the X or the Y axis and the reference voltage. So in this little example here, we would say that the difference on the x-axis is 0 and the difference on the y-axis is -2. And then that -2 tells us that the y-axis has been deflected forward, and therefore we want the wheelchair to go forward. I hope that made sense. So what we were left with was having to, in order to measure the position of the joystick in the X and Y axis, we need to take 3 analog readings. And as we're doing it, so we're looping through quite quickly, like many times per second. The thing is that you don't need like kilohertz type sampling on this because you're dealing with human interaction and relatively slow moving. So if you do it 10 times a second, the person isn't going to know the difference between 10 times and 100 times. But what we would have to do is take an analog reading on the reference voltage and store that as a reference value, then take an analog reading on the X and Y axes and determine the delta on those axes from the reference, and then that tells us our joystick position. Kind of. We also need to do some scaling. So you need to figure out the full scale range across X and Y axes for to know what sort of scale you've got to apply when you do the analog read. So what we came up with was, what I'll do is I'll do a bit of a a sequence through the different things we did, and you'll see how dodgy the early stuff was. Now, in order to break into the wheelchair control system, what we did was a little man-in-the-middle thing, I suppose you could put it. This is why it's called a breakout box. So normally you have the wheelchair control system, and then we've got the joystick over here, and the cable just connects straight in. So what we did was insert our box in the middle. We put a socket on one side and a cable on the other, and that way we could obtain power from the wheelchair controller, like the main controller, which is sent down through to our device and to the joystick, and we could watch what's going on with the signals in the middle, and then we could use them for our own purposes. Now, the very first application of this, the thing that we wanted to do, was to control a radio transmitter, like a FlySky radio transmitter, so that we could have Nick and Chris flying drones using their wheelchair joystick. So we looked at a few different ways of interfacing with the transmitter, and they have a trainer mode where there is a socket on the back. You can have two transmitters. So if you've got a trainee pilot and an experienced pilot, you put a buddy cable or a trainer cable between the two transmitters, and one of them becomes the main transmitter that sends the signal, and the other one just becomes inputs. So by flicking or holding a switch on the transmitter, you can switch between the controls that are in one person's hands and the controls that are in another person's hands. Now, the way FlySky transmitters work is that the signal that goes from one of those controllers to the other is called PPM, which is pulse position modulation. It's like PWM, but it's a whole series of PWM signals stacked into a packet. So the width of the first pulse is the PWM value of the first channel, the width of the second pulse is the value of the second channel, etc. So you can have like 16 pulses in a row, and the length of each pulse indicates the PWM value for that channel. So one of the first things that we did was to start reading the analog positions of the joystick and then generating PPM signals that we could send to the transmitter. And if you want to see a whole bunch of hot glue and craziness, this is what we did. So, in fact, before we even got to that, hang on, I'm going to pull this off so you can see what's underneath it. So the very first thing we did was this, which is an Arduino shield with a whole bunch of jumpers in the middle, and it's basically a breakout for the signal. What you can see here is just a pass-through cable. It's like a little extension cable, DB9 plug-in socket on each end. And this was a continuous cable. We just took the wire cutters to it, chopped it in the middle, and then connected each of the signals to this prototyping shield, and then bridged them through these little pin headers. So what this gave us is, and when these little jumpers are in place, it just bridges the pins straight through. So that gives us a really easy way to connect the joystick back up again into the original control system and then break out all of the signals. Because what we can do is, if we want to isolate any of the signals, we can just pull a little pin header off the jumper, and if you want to measure anything, you can put an oscilloscope or a multimeter in there, because all of the signals are exposed right on that little thing. So that's actually a really useful technique. If you have some kind of a control system that you're trying to interact with and understand how it works, make some kind of a little breakout that exposes all of the signals and allows you to isolate them, because it makes it much easier to work with rather than trying to solder up custom connectors and things. By doing this, you've basically got every single connection exposed, and you can manipulate it just by pulling headers on and off. It really speeds things up. takes a little bit of extra work at the start, but then once you've got a breakout like this, it's a really big time saver. It's a useful tool. So this is what we used to figure out those voltages that I was talking about earlier. We put a couple of multimeters on it so that we could connect this up to the chair and then see what was happening to the voltages on the different lines as the joystick was moving. And we figured out which lines were related to which axes and what directions they were going and that sort of thing. And then we figured out that it was this voltage offset issue. So the next thing to do was how to make use of this information. Now that we could break out from the connection and spy on it, we need to use those values somehow. So what I did was pass through. Now I could have used the Arduino headers for this, so I'll just get that over where you can see it. What I could have done is taken the connections, so these connections up here where you can see the little jumper wires plugged in are the reference X and Y axis values. I could have passed those through to analog inputs perhaps, but just the way we did it was that we jumpered it up and plugged it into another little shield. So at this stage we're really using these shields as kind of just like prototyping board, and added a couple more connectors. So this one I'll ignore for now. I'll explain that one in a moment. We'll get back to that. And so what we did with this is set up some voltage dividers, and in fact I haven't done this before on a live stream, but I'm going to try switching to a microscope and we'll see if we can get anything useful coming out of this. Much better. That, and let's go for microscope. Okay, so I just got myself one of those little Elgato game capture devices, and it's taking the HDMI feed off the microscope camera. And what you can see here, the black is, need something to point with. So the black cable here is the ground reference from the signal that's being passed to the controller. And then purple, grey and white are the three analog connections, VREF, X and Y. So what I'm doing here is those signals are being passed down to voltage dividers, which then go into analog inputs down here. So for example, well, where's one we can see? Let's see A2. What I'm doing just down under here, if I can get this cable out of the way, is that there is a voltage divider between, these are all surface mount resistors. So if you look down, hang on, I'll zoom in a bit. This is kind of cool, doing this on, I've never actually used this before, so let's see how it goes. Okay, so what you're looking at there is surface mount resistors that are bridging the pads on the prototyping board. So if you look just down there is an 0603 surface mount resistor. That's a 47k ohm resistor. And this blue wire, which comes from the other connector that I'll show you in a moment. So this is a signal coming in from a joystick. It goes through a 47k resistor, and then bridged from the bottom of that 47k resistor is another 47k resistor going to ground. So this is 3 holes in a row of the prototyping board with resistors just bridging across them. And then the row of blue wires you see at the bottom here are tapped into the center of those voltage dividers. So I'll, just to clarify that, I'm going to switch back and do it as a diagram, because I think that might make a little bit more sense than trying to look at it on the board there. So we've got, move the microscope. So what we've got is input. Like just say, take the x-axis as an example. It comes to a resistor, which is 47K, and then goes down to another resistor, which is also 47K, and goes down to ground. So the voltage that comes in at the top here, if the joystick is in the center position, might be 6 volts, just as an example. And because we've got an even voltage divider here, what comes out of here is going to be 3 volts. So it'll be half whatever the input signal is. So the variation on the actual signal is, I think it's just under 3 volts. So full scale deflection, which means that this x-axis value could be anywhere from, I think it's from 3 volts up to 9 volts, depending on which way the joystick is being pushed. So that means that the voltage we get coming out of the voltage divider is going to be anywhere from 1.5 volts up to 4.5 volts. And that puts it into a range which is ideal for measuring using an analog input on something like an Arduino. So we have, if you've got an Arduino running at 5 volts, you can then measure between 0 and 5 volts, ideally just a little bit less than that on both ends of the range. So by using this voltage divider, we can then connect this to an Arduino, which will measure the position of the joystick by measuring the analog input. So what you see on that breakout board is this circuit just replicated 3 times. It's for the reference, the reference, and then for each of the axes. And those little blue jumper wires are bridging over from the center of the voltage divider down to the analog input. Okay, so that explains why 3 of them would be there. But as you can see, we've actually got 6 voltage dividers here. And the reason is we wanted to add a second joystick, because one joystick gives you 2 axes, but to do something like fly a drone, typically you'll need roll, pitch and yaw. Or like to fly an aircraft, you need roll, pitch and yaw. In the case of like a quadcopter, even if it has something like altitude hold in the flight controller, what you'll need is like an altitude input. So you want to be able to move it up to a new altitude or down. You want to be able to rotate it, so yaw left and right. You want to be able to roll, which will then make you slide left and right, and pitch, which is up and down on the front back axis, will then make you move forward and back. So you need more than 2 axes to fly a drone. So we wanted to have the normal wheelchair joystick on, which in Nick and Chris's case is mounted on the right hand side. So on the armrests of their chair, I'll slide over so you can see. So my right hand sitting on the arm of the chair, and then the joystick is mounted so that they can control it. What we wanted to be able to do was also mount one under the left side, so that what they could do is use the 2 joysticks in their natural position with their arms on the armrests and have control over all 4 axes so that they could fly a drone. So, okay, what we did there was add a second input. And I'll switch back to here. So this socket that you see here is really just an extra socket for connecting in another joystick. It's So this is the socket that the first joystick plugs into. This, well, plug, whichever way around it is, and that's the plug that the second joystick plugs into. So with the 6 analog inputs, we could then read the 2 reference voltages and the 4 axes. So in use, this whole thing that you see here would have actually been plugged into an Arduino. I don't know if we've got a whole, because we've been through so much hardware, and then things keep getting pulled apart. This is a very early one. No, I don't have it here, but we've this was plugged into an Arduino, and what we then did was we could report out just on the serial console what the position of the joysticks were on all 4 axes, so X1, Y1, X2, Y2, and then we got on to generating PPM signals, and that's what this little thing is for. On a FlySky transmitter, it has one of these little mini DIN connectors. It's a 4-pin mini DIN, which is what is used for taking the signal in from the trainer or the buddy remote control. And so what we did was use the same socket, and that way we could work with a totally unmodified transmitter and a regular buddy cable exactly the same as it would normally be used. It's just that instead of plugging it into another transmitter, what we're doing is plugging it into this, and then the signal on here was being generated by the Arduino. And the Arduino itself was running a library which allowed us to generate the PPM message based on the position of the 2 joysticks. So we were sending 4 channels of data, and then the other channels we were just ignoring, just leaving them center position. So the receiving, so the other transmitter would just think that it had 2 joysticks that were then sending it commands. Now, this so far was actually quite a lot of work, and at this point we were still using little bodged up things with hot glue all over them and cables, and it was quite a mess. So we got it to the stage where it kind of worked, but it was quite crude, and setting it up was a bit of a pain because we had jumper wires hanging out all over the place, and it was a bit of work. And we also found some problems with PPM, and we ended up changing our approach to the way we connect to the transmitter quite significantly, but that's a different story. that comes a little bit down the track. So now that we got to the point where we had a proof of concept, we had this hot glued prototype, and we wanted to take that to the next stage where instead of having all of this stuff that was hand assembled, I wanted it to be on a PCB so it would be more robust. We could put it inside a case, and that would mean that we could take it outside more easily and use it for other things. So this is where we transitioned from the really crude investigation phase. It was just breakouts and trying to figure out what's going on with the existing control system of the wheelchair and turn it into something that is a little bit more usable and robust. So that's when I started laying out a board for it, and I'll show you what I have here is the result of the first version of this. So V1.0 is this big board here, and the idea here was to go as quickly as possible from the bodged together thing that I just showed you to a board that that was much more robust, but it wasn't necessarily more sophisticated. It's really just taking that bodged mess and putting it onto a PCB pretty much as is. There weren't really major design changes to it. So what we were still doing was using an Arduino for doing all of the processing and the sensing. And so what I did was lay out, essentially this is like a really big upside down shield. Now if I I find an Arduino somewhere. It's got to be an Arduino. Here we go. So there's an 11. So what I did when I was laying out this board was put down the footprint for an Arduino as if I was building a shield, but I mirrored it 180 degrees around the x-axis so that the Arduino would mount upside down. So normally, if you're looking at a shield footprint, it's designed to fit straight down onto the top of an Arduino. So when you're looking at a layout like that, the shield follows the exact same layout. It's going to have the power pins, like the power head is down here, D0 is up here, and it comes along in this direction. What I did with this one was the opposite. If you look at it from the top of the PCB, it's a mirror image of what an Arduino normally looks like. So you can see that the tail of the Arduino is over this side instead of being over this side. And what that means is that instead of this board plugging down onto the top of an Arduino like a normal shield, which would, you'd expect a shield would plug in like this, what we do is take the Arduino and turn it upside down and then sit it on top of this other board. So it plugs on, and what I did was use, I've just put stacking headers in here as extensions, and then you end up with, you can see that the bottom of this PCB here, and you turn it over and you've got the bottom of the Arduino there. Basically the two boards are facing each other and plugged in with headers, so upside down on the shield, I suppose you could call it. And that was just for mechanical clearance reasons. The case this was going into, I wanted to be able to mount this and screw it into the bottom. And so it's got little cutouts on the side that fit around the mounting stakes. Now the actual physical case that this goes into, I don't have it here. It's at Nick's place in another prototype, which I wish I could show you, but I don't have it here. So it had, typical plastic case. It had mounting stakes in the corners where screws go in to screw the two halves together. So the shape of this PCB is designed to clear those, and then I've got mounting holes here for mounting pegs that are in the board, so this could be screwed into place. And that's why I fitted the Arduino upside down. The base plate screws into the bottom of the plastic case, and that just gives it a really good secure mounting with the connectors at both ends, and then the Arduino just plugs in like that as like a little carrier board. Now the only real change that we made with the design between what you see here and what I showed you on the workbench is the isolation switch. So what we were doing originally with our first test was that we were just watching the existing messages and how the joystick interacts with the wheelchair and then reading the positions. What we wanted to be able to do was isolate the signal that's going back to the chair. Now this comes into a really big safety issue. So a wheelchair is really strong, they're really powerful. So in the case of Nick and Chris's wheelchairs, so with them in the chair, the total mass is, I think it's somewhere in the region of 240 kilos or 250 kilos. I may be a little bit wrong with that, but it's up there. Like the chair on its own is heading towards the 200 kilo region, and it's got really powerful motors in it and big batteries, and you could not physically stop it if you tried. Like if you were trying to hold the chair back, you wouldn't be able to. It's basically like a little tank or a bulldozer. And keep in mind that what we're doing here is messing with the control system and the signals that are coming from the joysticks that they use to drive that chair around. So if we cause any problems with those signals, we could potentially drive that chair into someone else. We could drive Nick and Chris into a dangerous situation. And we really didn't want anything that could cause them to go and and do damage to something or to themselves. So what we were doing with the initial testing was putting the chair into basically like an error mode where it wouldn't move. So we were taking the signal from the joystick and then redirecting it, but the chair itself wouldn't move even though they were moving the joysticks. So what we did with this version, which was the first one that was on a PCB, is we routed the control signals through this switch. Now we thought about a couple of options for how to do the isolation, and the immediate thing that came to my mind, of course, was some kind of software control. So what you do is you take the signals through here, and you could either use something like mechanical relays, or maybe just some kind of an electronic switch under the control of the Arduino. And you could then, if you were going into a mode where you're taking the signals and sending them somewhere else, you could then isolate the outputs so that the wheelchair won't move. But we decided to err on the side of caution, so we're a little bit paranoid for good reason. And what we did was we actually routed the signal. So if you look at this PCB, and I'll pull this up in Eagle in a minute so you can actually see it a bit more clearly. What you see here is two joystick inputs on your left, and so joystick 1 is the main joystick that normally controls the chair. Joystick 2 is a secondary joystick that we added, and the signal for joystick 1 passes straight through the board and comes out the output, and this goes to the main chair control itself, the controller. But what we did was bring the signal across and then through this switch and then back up, and this allows us to totally isolate the output. So we know that if we flick that switch up, there is absolutely no way that control signals from anything that happens on the board, from the joysticks or anywhere else, will end up making it out of this port and going to the controller on the chair, which could then cause it to move. Now the chair controller itself has some safety stuff built into it, and if it detects that any of the inputs from the joystick go outside the range that it's expecting, it puts itself into an alarm state and it just refuses to move. So basically it comes up with an error message on the screen of the chair and says, mini joystick failure, and the chair will just stop and won't go anywhere. And in fact, the only way to get out of that I know of anyway, is you have to turn the chair off and then turn it back on again, which only takes a moment, but it means that once the chair goes into an error state, it's safe. It won't do anything unexpected. So by flicking this switch, we are isolating the chair from the joystick, and because the chair signal is now floating, it basically drops to 0 volts, and the chair immediately goes into an error state, and it'll just freeze, won't move, and then we can do whatever we want with the signals from the joysticks and then send them somewhere else. So what you're looking at right here is version 1 of the PCB, which I do have in Eagle, but I'd have to roll back in Git to get to that version. What I'm going to show you now is version 2 of the PCB, which is just an extension of this. So what we found was we had a regular size Arduino plugged in here. In fact, what we were doing was, for a little while, we used a Leonardo, which I'll explain in a moment, so that we could do game controller emulation and things. But we only had 6 analog inputs. And what we found was, as we were generating the PPM signal coming out of here, going to the transmitter, we had situations where the joysticks were not centered. And the way FlySky transmitters work, and I assume others, but FlySky is what we've been using, is that the trim on the joystick positions does not apply if you are taking the input from some external buddy connection. If you adjust the trim on the joystick, it only applies to the joysticks on the controller that they're actually physically on. So we needed some way of doing trim, and we thought about doing it in software, but that's just a real pain because it means you've got to sit there at a console and change values or something. We wanted to replicate the trim on a remote control, so you just twist the knob and adjust the 0 position or the center position of an axis. So we needed 4 trim inputs for the 2 inputs each on the 2 joysticks. So that means we'd run out of analog inputs, and we needed to go for something that had more inputs. So if we switch over to Eagle, I'll show you where we ended up with that. And what you can, hang on, which one is this? No, I'm looking at the wrong one. That is version 3, which we will get to in a moment. So this is the replacement version. So this is version 2, which replaced this one. And the major difference that you can see is the footprint has been extended, so it takes a Mega style Arduino instead of a regular, like Uno size Arduino. And also along the bottom, you can see that there are a bunch of extra inputs for a trim for the 4 axes. There were also a couple of other minor changes in terms of the way the power system works. But if we zoom in and have a look on here, let's switch back to the schematic just for a moment, and you'll see how this is working. So we've got the 2 inputs on the left. This is the primary joystick input, and that's the one that's normally used to control the chair. And this plug, which looks like a serial connector, but isn't, it's the one that has the analog outputs coming from the joystick controller. So what we've got is a ground connection. So there's a ground reference. There's 12 volts. There are actually 2 12-volt connections here, and that is a bit of a strange effect of the way the chair is set up. I won't get into that right now because there's meant to be like a 12 volts in and then a 12 volts out, but in practice they're just bound together in devices like the joystick, so we just bound them together as well. Then there is a detect, which allows the chair to detect that a joystick has been plugged in. And N6, we don't think this is actually being used for anything. There's a connection here, so we just pass it straight through without caring what it is. So what you can see is the input on the left and the output on the right. Input being the joystick, output being the existing chair controller. And with the switch in the middle for isolating the speed and direction. So speed is y-axis, direction is x-axis. And so speed comes in here from the joystick, goes through the switch, which allows it to be isolated, and goes out to the same pin, so pin 1 at the other end. So with the switch in the on position, these signals all just pass straight through our little breakout and aren't affected in any way. So then what we've got down here is the voltage dividers. And what I did with this was use a pair of 47k resistors. This was a bit of a judgment call because there is a potential bias issue here with the signals that we are measuring. And we did a bit of experimentation with this to see what would happen. So what you have to do when you're designing a system like this is think about the bigger context of what's happening to these signals after they pass off onto other parts of the system. So let's just take reference as an example. So the reference voltage comes in here out of the joystick, passes through, and it goes through to the chair controller. So the chair controller has to measure that voltage level, which will be 6-ish volts. But you have to ask yourself, how is that going to actually happen? Will inside the chair controller, presumably it's got something like an analog to digital converter, which is reading the voltage on that input. Now, maybe they have a voltage divider in there. Maybe, well, the thing is that we just don't know. The chair controller to us at this stage is a black box, and what we're doing is we're passing that reference voltage to it, and in measuring the signal, we could be changing it in a way that is then going to mess up the chair controller. So if they're doing the classic thing and essentially doing the same as what we're doing, they're taking the signal, applying a voltage divider, and then feeding that into an analog to digital converter in order to read the current signal. What we're doing with our voltage divider is biasing that line. So the reference line comes along here, passes through, but we are tapping into it using our voltage divider. Now look at the way a voltage divider works. If we just look at this section right here in the middle, we've got the signal coming in from the top, going to a 47k resistor, and then we've got another 47k resistor going to ground. So what that gives us is the equivalent of 94k going between the signal and ground. But there's nothing corresponding pulling it up, like trying to offset that bias. So in effect, we could be pulling the voltage on that reference line down a little bit, depending on exactly what's going on inside the controller. Maybe they've got a voltage divider that is very strongly biased, like perhaps they've got like a pair of 1k resistors, which would be an extremely strong bias in a voltage divider. But maybe they have a really high impedance input. They might have like a pair of 200k resistors, and that would be a very weak bias on it, which means that effectively we would be varying the signal in a way that would be detected by the controller, and that's not what we want. We want the signal that comes through to the main chair controller to be totally unchanged. Otherwise, really bad things can happen. Like one of the things, Nick and Chris were experimenting with this before I got involved in the project. It was some years ago they started experimenting with trying to, they actually set up an old wheelchair, and they were trying to set it up with a remote control. Basically, they were turning a wheelchair into a remote control robot. And what they found was that they had problems with drift. So the wheelchair would be, when they were sending no signal to it, and the position was meant to be just centered like center joystick, the chair itself would start moving. And that's because there was like a bias being applied to this input, which was then making the chair controller think, oh, they're pushing the joystick in that direction, so I better move in that direction. So one of the things that we needed to be really careful about was that we didn't do anything that would cause the chair to think that there was an influence on that signal. Okay, so you might right now be thinking, but that doesn't matter because you isolate the output from the chair by flicking the switch and then it can't move. But the scenario I'm thinking about here is ultimately we want to leave this device permanently attached to the chair. So we want it to be in two possible modes. One is pass-through mode, where we are not using the signal in any way. The joystick is just controlling the chair as usual. There's no variation on it. And the second mode is we want to isolate the output to the chair and then use the signal ourselves and send it to something else. But what about that first mode? So if we've got our box still connected and we are passing the signal through, and we want the chair to be behaving exactly as the factory intended, in that situation, we can't afford for the signal to be varied in any way. The chair has to behave in a perfectly normal way when it's connected. So that's why I was a little bit worried about these voltage dividers. And so with this pair of 47k resistors providing 94k of pull down, which is fairly weak, to ground, that has the potential for biasing the signal as the chair controller sees it. And what we did was experiment a little bit. Nick and Chris have their old wheelchairs still there, and so what we did was pull out one of the old wheelchairs and connect up to it with this little control system, and then oh yeah, make me laugh said, famous last words in every one of my projects, behave perfectly normal. Yes. Um, in this particular case, I'm even more paranoid though, because if it doesn't behave perfectly normally, there is the potential for injury and death. So um, so what we did was we actually tried a couple of different values of resistor. We tried some much lower value resistors. I think we might have even tried down to like 4K7, like a pair of 4K7, which gives us 9.4K of bias down towards ground. And at some point we did see that there was a bias being applied and creep happening on the chair if we did that on just one of the inputs. So there are two things we did. One was we then increased the value of the voltage divider resistors so that it would have less bias. And the second thing is we discovered that if you do the same bias on all of the lines, basically it doesn't matter because they're all being affected in the same way, and the reference voltage is also being affected in the same way. So what we did was we took the resistors up, and at 47K there's no detectable influence on the chair's behavior. When we apply the voltage divider to just one of the axes, say the y-axis, so speed in, and we apply a voltage divider and we leave the other two control signals totally unmodified, untouched, just pass through. So effectively we just take these resistors out, and then there was no effect on the chair. And the other thing is that by having this voltage divider on the reference voltage as well as on the x and y axis voltages, it means that the reference voltage is also potentially slightly biased down, but it's biased down exactly proportionally with the other axes, which means that as far as the wheelchair controller is concerned, it doesn't matter that the voltages come down slightly. The difference between the axes and the reference is still the same. So it's just moving the scale very fractionally down by a tiny fraction of a volt. And the result was that we discovered that we had no problems at this point. Okay, so Steve Cody said, would it not be safer to use high input impedance differential input AD converters talking I2C to the Arduino rather than passing analog signals about? Yes, Steve, you're correct. So what Steve is talking about there is the reason that we have these voltage dividers is that the analog inputs on an Arduino are they're basically like a little charge pump or a bucket brigade ADC, and what they do is allow you to measure between close to 0 volts and close to the operating voltage of the processor, which in the case of a typical Arduino is 5 volts. So if you have an input to the analog input that is between 0 and 5 volts, you can measure it. But because we're dealing here with a system that is nominally operating at 12 volts with 6 volts as the midpoint reference voltage, and the voltages that go above and below that, the range most of the time is actually outside the upper range of the analog input for the Arduino. So we can't just take the X, Y, and reference signals and pass them straight into the Arduino's analog inputs. We have to do something with them first. But Steve's suggestion is to use a different type of analog to digital converter, which can do something like differential measurement, and then we talk to it from the Arduino and basically ask it for what its current value is. So you can get little differential ADCs that are I2C as Steve suggested. So what we could do is put a separate ADC chip on here, and then there would be a very high impedance on that input, which means that instead of having the 94K bias, which we've got with this this voltage divider, it could be many megohms of impedance on the input for the ADC. So it really shouldn't affect the signal in any way. So the short answer is yes. That is a better way to do it, and that is quite likely how we will end up doing it in a future revision. But at this stage, what we had got to was just rough measurements and investigating how the system worked. So we hadn't yet got to the stage of really optimizing the circuit and trying to make it 100% production ready. So Steve, great suggestion. So the result of this is we could measure the speed, direction, and reference voltage on the Arduino connected on these headers. And you can see that there is this set of voltage dividers up here, and then down here there is another set of voltage dividers for the second joystick. And essentially what we've got is two copies of the same thing going into those analog inputs. So we've got those 6. Then what we have over here, I'll just gloss over this because it's not that interesting. We have the mini DIN header here, which is a 4-pin plus a shield or a mount, and that's coming out on D8. So from the Arduino we can generate a PPM signal, send it to pin 1 of this connector, and then we can send that on to a remote control transmitter. That's just one link and some software, so it's not particularly interesting. Then, so you can see down here I had some notes to myself. So in the schematic while I was working on this, I actually just grabbed the text tool and then stuck some notes in just as they came to me, so that next time I'd be looking at the circuit, the notes would be right here in front of me. So one of the options was to add another AT-mega for the trainer port. The reason we were thinking about that was to get the timing correct, because the PPM timing could be a little bit critical. Turns out we didn't need it. And this question here is about, will the voltage dividers bias the lines enough to cause a problem for the chair, which is exactly what I was just talking about. So what I did was, and I had the note, maybe add equivalent pull-ups above each line, so that we would be offsetting the bias, which is another way that you could minimize this. Still not ideal, because effectively you're damping the signal, but I was considering that as an option. And also, because we have a voltage divider here consisting of a couple of 47K resistors, the analog inputs on the AT-mega, because it's got this little bucket brigade input system on it, I won't go into that right now. In fact, I did a really detailed explanation of how that works in my book Practical Arduino, so I might talk about that some other time. But the way the analog to digital converter works, it requires a certain amount of current coming into the Arduino's digital pin in order to adequately resolve the level. It's a successive approximation system, and if you have an input impedance that is greater than 10K, you may not get quite enough current going into the analog input in order to get an accurate result. So I just made a note to myself there that the analog inputs on an Arduino are optimized for sources with an impedance of below 10K. So if we had used a pair of 10K resistors on that voltage divider, the analog input would be perfectly fine. Now, one way around that is that you just sample for longer. You can change that by changing some registers in the AVR so that you're not sampling as quickly on the analog input, and it gives the input more time to resolve what the voltage is on that analog input. So we haven't done that either. But notes for myself for future reference. So the other thing that we did, the other change on version 2 with the Mega attached to it compared to version 1, this one that I just showed you with the Uno, is that we needed all of those extra analog inputs for trim inputs. And right here, super crude, I actually just pulled these out of the other prototype, which is at Nick's place right now. In fact, I'll show you a PCB. Excuse me. So this is a little stack of PCBs for the version 2 board, and this is not populated. Oh, thank you from Kronos. So where am I? I'm at camera. So this is the version 2 PCB, and you can see it's got these extra connections along the bottom here, which are the analog inputs for the trim, and up here you can see the positions for the voltage dividers feeding down to the normal analog inputs. So these headers that you see here, are for this little mess. So this is a mess of potentiometers, and we've got one. What I did was I just jump it around the ground and VCC references. So on there we've got one side goes to 5 volts, the other side goes to ground, and then the middle is the wiper on the pot, and then each of those goes to one of those analog inputs. So these were screwed into holes in the case, and what that allowed us to do was, so this was all attached and in the case. So what we could do then is read the position of these pots using analog inputs. I'll switch back to the PCB layout. It's easier to see here than looking at the PCB with me holding it up in front of the camera. So the inputs here, for example, X1 trim, that one just goes along to analog input 8 on the Mega, and then we've just got ground and IRF, which in this case is 5 volts going to each of the pots. So once again, the pots form a voltage divider. A variable resistor or a potentiometer is just a variable voltage divider. The voltage between the top and the bottom is constant, so in this case it's, I can't even remember the value. The value in this case doesn't really matter that much, probably like 10k. So it's 10k of resistance between the top and the bottom constantly, and then the wiper, the center position, will vary somewhere between the top and the bottom voltage depending on the position of the knob. So by reading of the position of those 4 pots, it meant that in software we could then apply compensation values for each of those 4 inputs from the joysticks, I mean. So the X1 trim could then be used to apply an offset value to the position of the X-axis on the first joystick to center it as far as the output is concerned. So what we could do is plug it into a FlySky transmitter, and then if you have a model or something that you are controlling, when the joysticks are all in the neutral position, you want the model to be neutral. But if it's like moving, say you're controlling a robot and it's turning in one direction or driving forwards and backwards, you just use the knob for the appropriate axis and you just turn it until the model itself is zeroed and it's behaving the same way that the joysticks are. So that gives you a very quick and convenient way to adjust trim out in the field. But that actually had some problems, and there were problems that we could possibly have overcome in software, but we ended up taking a major left turn with the design at this point, because we decided that what we were trying to do was solve a general problem for in a specific purpose or a specific application. And what we needed to do was solve the problem in the right place. Basically, we were trying to solve the problem in the wrong place. I'll try to figure out how to explain this. So what we have that you can see on the screen here is a single board that takes input from joysticks, passes one of the joysticks through, but not the other, and it generates PPM signals for a FlySky transmitter. But that's it. If you want to use it with a FlySky transmitter, that's fine. But what if you want to do other things with it? And solving problems like the trim is very specific to generating the PPM signal, which is then linked to the transmitter. And that's really about trying to replicate the behavior of a transmitter that has trim adjustments on the joysticks. And the thing is that for some things you don't actually want trim adjustment. And we found that because we were at this point trying to use this for different purposes, the trim was actually being annoying. And so we decided to split the design. And in some ways this seems counterintuitive, and I'm still not entirely convinced we've made the right design decision, but we'll see where we go. So my original objective here was that we wanted it to be a device that was permanently attached to the chair, so super convenient. We wanted it to always be ready to go, but still trying to think of how to explain this problem, this design problem, which is kind of important. If we set this up to work with a specific FlySky transmitter, then it would not work for other purposes like passing data out through the USB port to do things like emulate a game controller. And we wanted to make the part that stays on the chair and is permanently connected as flexible as possible without having to change it for different purposes. So if we want to pass signals from the wheelchair to a computer to play a computer game, so say Nick and Chris are sitting in front of their computer, they've got the screen in front of them, we want to be able to plug in USB to the computer and have the system emulate a game controller so their joystick can then be used to play the game. But that doesn't need any of the trim controls that are specific to a FlySky transmitter. So, and they just get in the way if you are then wanting to adjust the output, so you're wanting to make sure that the position of the joysticks is being faithfully represented at the other end. So we came up with this idea that what we would do is split the part of the design that integrates with the wheelchair and then reads the signals from the part that integrates with whatever the target device is. And the thing is that there could be many, many different types of target device. So we might want to fly a drone, or we might want to emulate a game controller, but we might also want to do lots of other things. We might want to send controls to a robot, or perhaps, which could be remote controlled, or it could be something like a robot arm attached to the wheelchair, which we have direct electrical control over. So we want to send those signals to the robot arm so that an operator of the chair or user of the chair could drive the chair somewhere, control the arm to pick something up, and then either just hold it and then drive it somewhere else, or pick it up and then put it on the tray table on the front of the chair. And so the requirements for interfacing with a device like that are totally different to interfacing with a PC to play a game, and totally different to interfacing with a FlySky radio transmitter to fly a drone. And so if we tried to integrate all of those different outputs or those different control methods into this system, we would end up with something that is really complicated on the chair and potentially not very extensible. So our plan was to try to make little interface modules or some kind of adapter that we could make very specifically and as simply as possible for each of the target devices that we want to link, and have a standard control breakout attached to the chair that doesn't understand anything about what it's trying to control. It can just read from the joystick positions and then send those values to something else, and then that something else can take care of interfacing with whatever device you're trying to control. So we kind of modularized it. Maybe that was the simplest thing. I should have just said that in the beginning. So that then led to a major rethink of this design and a bit of an optimization of it. And that took us to the CB Mini, the Chair Breakout Mini. So version 2 that you see here is Chair Control Breakout version 2. And another part of the decision around this was that we got this to the point where it was actually useful. We were doing cool stuff with it. Like Nick and Chris were controlling little combat robots and doing other cool things. And we want to be able to apply it to different types of situations. Like there are people who use wheelchairs who have only a single joystick. There are some with 2 joysticks. As I mentioned, there are people with foot controls and different things. So we wanted to make it as flexible as possible, which also led us to the modularization thing and led us to dropping the second joystick input. And I'll switch to the next design and I'll show you kind of why and what we have in mind. So we've got that one, the chair breakout, and then if we go to CB Mini, which is this one, there are a couple of things about this. Firstly, it's much more integrated. There is no more Arduino plugged in on the carrier board. Secondly, it's much, much smaller. And I've got one, well, I'll show you a fully built up one in a moment. But basically, in terms of volume, it ends up being about 1/3. So like that's the original chair breakout. This is the chair breakout mini. It's approximately 1/3 of the volume. And it has everything on board. So it's got a processor. It also drops down to being only one input. And we did that because we wanted flexibility in terms of the inputs that we could take. Now, one of the things that's often done on wheelchairs is to use a thing called a button box, and that is a generic input device where you have a box with typically 3.5mm like headphone sockets on it, and all it does is detect whether those have been shorted. So what you can do is you can make different types of input, which could be something like a really big button that's easy to press, or it could be something like a proximity switch, like a capacitive touch switch, or it could be all sorts of different things. It could be like a photo interrupter type switch. As long as it can provide a switched output that goes into the button box, that can then send a signal on to something else. And you might want to use that, for example, to have a very customized input or a specific input. If you are playing a game, you have the joystick for X and Y, but then you need like fire buttons and weapon select buttons and whatever else you might need. And so we wanted flexibility for other types of input as well. So conceptually what we did was think about this, instead of being a single self-contained device, think of it as being part of a system or a network. And this board that you can see is designed to read from a joystick and then pass its values on, but it doesn't necessarily need to know what's being done with those values. And it also doesn't necessarily need to be comprehensive in terms of having two inputs, because we know we need two joysticks for a very specific application. Perhaps you need one joystick and you need some button inputs, or you might need one joystick and one foot control system, or a sip and puff interface. So you might have all sorts of different combinations of things, and we wanted to make it very modular. So we really focused this design on just reading from a joystick, passing that joystick value through to the main chair if it's required, and then passing on the values of the joystick to whatever else it might need to be. So going to the schematic here, once again we've got an input on the left, so we've got the joystick connection on here, and you can see that this part of the circuit is basically the same as the previous generations. Joystick plugs in there, chair controller plugs in there, and we pass the signal through from one side to the other. We also have voltage dividers coming down off here so that we can read speed, direction, and the voltage reference. And those go down to the ATmega 32U4. So it's the same processor as on an Arduino Leonardo. And we chose this particular processor because it allows us to do HID emulation, which is human interface device emulation, which is critical if you want to pretend to be a joystick or a game controller or something. And even though we were thinking in a modular point of view, we want to be able to have different output modules to interface with different target devices. We wanted as a base, like just for this device on its own, to be useful to output HID, like to be able to do HID emulation, so that we could use it as a game controller input on a computer, or a joystick, or a keyboard, or whatever we want it to be. So that's why we chose the 32U4. And so because we don't have trim anymore, and we've only got the single joystick input, it means that we just have those three analog inputs, A0, A1, and A2, that go through to the main processor. So then we've just got some status LEDs, nothing particularly interesting, ICSP header. The power configuration is kind of strange and interesting, so I'll explain that once we are back looking at the PCB. And down here in the bottom left, we have a couple of chips for a CAN bus interface. So this is also kind of an interesting part of it. We were thinking about if we wanted to take multiple modules and connect them together into a bigger system, how should they communicate? And we talked about quite a few options. So, for example, the first obvious thing we thought about, may not seem obvious to you, but it was obvious to us because of where our heads were at the time, was to send ppm from this device. So we would read from the joystick, and then it would generate ppm signal that would go out to whatever else needed to read it. And then we could decode ppm at the other end. But the problem is that that doesn't really work as a bus. It only works as like a point-to-point connection. And we might have two joysticks, and they're both sending signals about their XY positions. So then we have two blocks of ppm signals, which means two sets of wiring. So we pretty rapidly dismissed that idea. And we thought about using other communications methods. And the more we looked at the way the wheelchair wiring is set up, the more we realized that CAN bus is probably the most appropriate way to go. So on a modern wheelchair, they typically already have CAN bus. They're using that to communicate between, say, the motor drivers and the main computer that's coordinating the chair, and the user interface and different parts of it. So there's already CAN bus on it. Basically, a wheelchair is like a car without, a body on it. And in terms of its technology, it's very car-like. It's like an electric car, basically. And So there's already CAN, which means that it opens up the possibility that if we make a device that can communicate with CAN bus, we may be able to integrate with the existing CAN, even if it's just to read signals. For example, it might be useful for us to be able to watch battery status messages that are passing along the CAN bus so that we can do something with that. And ultimately, we might want to inject signals onto the existing CAN bus, but it just seemed, even if we stay totally isolated from the CAN bus on the chair, it just seemed like an appropriate bus to be able to connect multiple modules together in a very robust way. It's so just by way of background, for those of you that have never heard of CAN bus, CAN stands for Controller Area Network, and it's essentially a high-speed serial communications method between devices that that might be in like a really electrically noisy environment. And the original application for it was vehicle communications. So when you have a car with an engine management system, the engine management system needs to communicate with other devices around the car. So it might need to communicate with the dashboard, so like for control signals and things, and lots of other things. So CAN is used as a communications method between different devices inside your car. And if you've got a car that was built anytime, probably in the last 20 years, it's pretty certain that's got CAN bus built into it, and it will have many devices that are all talking to each other over CAN bus. So CAN is usually considered to be like a vehicle communications system, but it's also gained a lot of traction in industrial applications because the way CAN bus works, it uses a differential signaling system where you have two wires and they are high and low signal. And so with most communication systems, what you would do is have like a reference voltage, typically ground or 0 volts, and then you have a data line. So if you're looking at a serial communication system, I'll just see if I've got an example over here. Okay, so USB isn't a great way to use it, a great example to use. Okay, I think it'll make sense if I just explain it. So what you do is, on a typical serial port, which is connecting between two devices, you have a common ground connection, which is your 0 volt reference, and then you have a TX and an RX. And the TX is where you send data, the RX is where you receive data. So your TX pin is connected to RX at the other end. And if you want to send a high value, then maybe you take your TX pin up to 5 volts, and then at the other end, they see it's at 5 volts. But that 5 volts is relative to the ground. So you've got a common ground connection between these two devices, and then you've got a signal which varies by a certain voltage above that ground. That's okay if you've got devices that are fairly close together and you've got the grounds very tightly bound together. But in an industrial situation, that can be a real problem because you can have electrical noise that will cause the voltage to fluctuate. Imagine you have a serial cable, a traditional serial cable with a TX pin and an RX pin and a ground, and it passes by a really big bit of machinery. It's just got a big electrical motor in it. So big coils passing high current, and it's generating strong electromagnetic fields. What can happen is, even if your ground connection, say your 0 volt reference between the two ends of this communications link are consistent, so they're strong, your 0 volt reference is good, you might have a line that comes out of the transmit on one side, goes into the receive on the other. That voltage could fluctuate based on electromagnetic fields that are around it. So if you've got a big bit of industrial machinery and it turns on or it turns off and you get a big spike in the electromagnetic field, the voltage at the other end, at the receive end, may not be 0 volts or 5 volts. It could be, no, it could go positive by hundreds of volts, or it could go negative. And so, hang on, station 240 said Q&A at the end, I assume. Feel free to ask questions. I actually really like it when it's interactive. So if you want to ask questions about things that I'm talking about or I'm not making sense, say so. I'm probably not making sense. So back to the serial communications. So what that means is that at the receive end, it's not seeing a signal that is either 0 volts or 5 volts, which typically you would think of as being data like bit 0, a 0 value or a 1 value. It might be seeing 2.4 volts for a moment. And does that mean that it's now considered 0, or is it electrical noise? Is it fluctuation? Or maybe the input voltage suddenly goes up to 27 volts and boom, you've just blown the input on your microcontroller. So CAN is a way to work around that problem. And that's what because it's a differential signaling system. So the way differential signaling works is instead of having a ground reference and then a data line, what you do is you have 2 signals and all you care about is the difference between the signals. So if you have, so in the case of CAN, it has what's called CAN H and CAN L, or CAN high and CAN low. And at one end of the line, you can drive them so that they are very different, or you can drive them so they are together. And if you are passing the signal over a twisted pair wire, so you've got 2 wires and they've been twisted together, what that means is that if it passes by a big electric motor and you get a voltage spike, it will apply the same voltage spike to both of the signals approximately equally because they are twisted together. And you won't get one of them spiking up and the other one spiking down or staying the same. So you might get a very big voltage spike and it's applied to both. So what happens is that relative to ground, like just 0, if you shoved a stake in the ground and you measured that as 0 volt reference, you might all of a sudden have, say, 1,000 volt spike applied to your wires, but they both go up by the same amount, and the difference between them is still the same. And that means that at the other end, at the receiving end, which is only measuring the difference, it's not measuring it relative to ground, it doesn't care. So it means that it's incredibly resistant to electrical noise, and you can run a very long wire without any ground reference and pass it through a noisy environment and it'll still work. So this design was originally for automotive systems, but because of this characteristic, it became really popular for industrial control systems as well. So you'll find that many big bits of industrial equipment use CAN bus for communication between different things. So there might be, for example, a really big actuator or a motor attached to the equipment, and it has a CAN interface. So, with most motors, we're used to, even a smart motor, you might be used to, say a stepper. You'd have a digital input, a digital interface that's got step and direction pins, and then we're used to generating a signal that we use step and direction to make this stepper motor turn the way we want. In an industrial situation, you can't expose that step and direction on a long wire because you'll get random signals coming into your motor. So what they do is they have the controller directly on the motor itself, controlling the stepper or the servo or whatever the actuator happens to be, using whatever it needs, but it will expose a CAN bus connection. So what you do is you connect your main machine controller to the actuator using CAN, and then you can send commands to it and say, move to this position or move at this speed and direction, and the actuator will do it. So the more we looked into this, the more we thought this is ideal for our objective of creating a series of interconnected modules that could be connected and disconnected on the fly that pass messages between each other, and without the overhead of going to something like a computer network. Like the other thing is you could say, okay, let's just make it Ethernet, and you have modules that connect by Ethernet, but then you need Ethernet switches, and it's just a whole lot of overhead that you don't need. CAN bus is designed for situations that you don't need to pass the data at the same speed as Ethernet, but you still do need to pass messages fairly quickly. So on CAN bus, it's quite normal to get a megabit a second of data throughput on a wire that is 100 meters long or longer through a noisy industrial environment. And there are many microcontrollers now that have CAN support built into them, and ultimately we may well switch to one of those. But for this stage of the project, and this is still very much work in progress, what you're seeing here is the third iteration of the PCB, but it's still got plenty of room for improvement. Like we could switch to an external differential ADC, as Steve suggested earlier. We may well end up replacing the MCU with something totally different, maybe to have native CAN support. We may want to go for a 32-bit MCU. So what we did as this stage is we use external CAN bus chips. The processor that we're using, the 32U4, does not have built-in CAN support, but it does have other common things like SPI. So what you can do is use a CAN bus transceiver chip, which you can communicate with using SPI, and the CAN transceiver chip takes care of all of the details of how to talk on the CAN bus. And commonly there are two chips that are required to do this. One is the CAN transceiver, and then the other is the CAN driver chip. And the driver chip is what takes care of the generating the voltage differential signal and actually connecting to the wire that you use for the physical interconnection between the devices. The CAN transceiver is what takes care of the logical structure. So how to buffer up the messages and then send them out at the correct clock speed and all of that sort of thing. So in a lot of designs you will find that CAN consists of two chips if it's external to the microcontroller. There will be the CAN transceiver, takes care of the logic, and the CAN driver, which takes care of the actual physical connection. And that's what you're seeing right here. So this chip up here, which is the CAN transceiver, so it's the MCP2515. We have SPI connections over here to the main processor. So we've got MISO and MOSI, so master in, slave out, and master out, slave in, just the two directions of the serial communications. We've got SCK, which is the clock pin, and we've got chip select, and chip select in this case is connected to D10. And with SPI, chip select is used to select which of the devices on the SPI bus that you want to talk to, because on many designs there will be multiple devices on SPI. You might have, say, an SD card, and SD cards speak SPI natively. You might have an Ethernet interface, you might have an ADC that talks SPI, you could have a whole lot of different things. So the chip select line allows you to turn on one of those devices at a time and say, I'm going to talk to you now. And then it wakes up and then you can talk to it. And then you disable that one, you turn on another one, and then you talk to that. So D10 in this case is just used for chip select. So Ecognito3 asked, why hasn't it been combined into one chip? Why two chips? Okay, I actually don't have a specific answer for that, other than I believe that the driver chip can be replaced with different driver chips for different situations. Like it depends on the type of interface that you're using as the connection between the devices. So you might want to use the same logical driver with a different driver chip? That's actually a question I've wondered myself. And with MCUs that have CAN support built into them, they're just based on what I've seen, what they typically do is they integrate the part that is currently in that that transceiver chip. So this MCP2515, the one that does all of the logic and takes care of sending out the bits at the right frequency and that sort of thing, and CAN controller and CAN transceiver. Okay, so sorry, station 240. I had my terminology wrong. So the CAN controller is this one, which does the logic, and the transceiver is the driver, which is the one that integrates with the actual hardware, like the external connection. So the microcontrollers that have it integrated typically have the functionality of the controller integrated into the MCU, but then you often still need the external transceiver chip to take care of the electrical connection. So maybe there is a very specific reason for that. I would be interested to know. So Station 240 has done, and eCognito 3 have, Station 240 has been doing work with CAN bus, so maybe they have some insight into what's going on here and why it's preferable to have the transceiver as a separate chip. So, cool. An answer from Station 240. The chip connected to CAN needs to be resistant to power surges from noise or accidental connections to 12 volts, 48 volts, 400 volts. Yeah, so it's an isolation issue. That definitely makes sense. Yeah. Okay, so what we've got, where are we up to? I've been blabbering for way too long. Alright, so we've got the main controller, it's got a CAN interface on SPI, we've got USB, and because we're using a 32U4, we don't need a USB to serial converter chip in here. We're just using the built-in USB support of the 32U4 to talk to the USB socket. Now, one thing about this USB socket, I've designed hundreds of boards, and this is the first time in my life that I've ever used a USB-B connector, which is one of those big square things. It's this one, the same as on a typical super cheap Arduino. Normally, I can't stand these connectors because they're physically very big, but in this case, we ended up going for that connector because I wanted something that was super robust. A couple of reasons. Firstly, this is going to be on a device that's physically attached to a chair, and when it's being set up and connected to a computer, the actual connection itself is most commonly going to be made by a carer. So the person who uses the chair would probably drive themselves up to a desk with a computer on it, and then they need the USB cable plugged in so that it can control the computer. Now, if you use something like micro USB, it's a very small connector. It's kind of delicate, and you can do things to try to make it more robust, but it's always kind of fiddly. Like if you've got a mobile phone and a cable, you can pick it up and you can get the alignment right and you can push it in and you're probably not going to damage it. But if you've got someone who is like crouched down beside a chair and the connector is in a fixed position, so you can't get it out where you can see it, they've got the cable in their hand and they just want to shove it, jam it in and make it go in. USB-B is actually a really good solution. It's physically quite robust, and it's really obvious which way around it goes in. You can put it in without looking at it, like you can just put it in and twist the connector until it drops into place, and so there's less likely to be problems with asking someone who doesn't necessarily know anything much about the system to grab the cable and plug it in. You can just say, grab that cable, plug it in there, and they can figure it out. So the other thing is thinking about the danger of moving the chair while you're still physically tethered to something and potential damage. So our plan is that when the system is mounted on the chair, we want the USB socket to be facing forwards, because at the end of a session, say you're in the chair and you've been playing a game for a while on the computer, and then you're finished and you switch the chair back to mobile mode, press reverse on the joystick, the chair backs up, and you've got 250 kilos of tank that you're sitting on, and rips the computer straight off the table. So if you haven't taken off the USB connection. And either Chris or Nick, I can't remember which one, has actually done that before. Like they've been tethered, their chair has been tethered to a computer and then backed up and pulled the computer off the bench because nothing is going to stop that chair. If the cable doesn't come out by itself, then you've just dropped your computer on the floor. So what I wanted was a connector that even from a little bit of an angle, say the cable is coming out at a slight angle, if you apply pressure to it, like you pull on it, the connector is going to pop out. It won't stay jammed in there and then rip something off the other end, off the bench. So I did the thing that I never thought I would do, and I stuck a USB-B footprint on a board and ordered myself some USB-B connectors, which I had managed to avoid all these years. But here we are. So, okay, so catching up on a couple of things. Station 240 says, the micro I'm using has the controller built in, but still needs an external transceiver. Yeah, that's what I've seen as well. Just looking around at microcontrollers with CAN support, I haven't actually seen one that has the transceiver built in. But I'm interested to know, Station 240, what microcontroller, if you don't mind sharing, are you using? I'm curious to know, because it sounds like you've done a fair bit of research on this, and yeah, I'd appreciate your advice on what is worth looking at. And there's a comment from MC Brizrat, who says, hi, 480p stream at 2018, really? And the answer to that is Telstra, which is the local national telco here in Australia. And I am on the fastest connection that I can pay for at any price in my physical location, and it's still rubbish. I'm on a Telstra cable connection. And for those, I would happily pay double what I'm paying now to get a faster connection, and I just can't get faster uploads. So we're stuck with this. My stream health little indicator in the YouTube streaming thing is mostly on orange, saying stream health is not entirely healthy. Sometimes it flicks to green and then the resolution goes up, but a lot of the time it's just maxing out my upstream bandwidth. So, wow, I'm heading towards 2 hours and I'm still on this one project. But it is an important one. It's the one that I've been spending a lot of time on recently. So, okay, so the physical board. We have the main MCU up here, 32U4. We've got the voltage dividers over in this area on the top left. So the joystick input comes in here, and then it feeds through to the output over here. So that's the pass-through connection for the joystick going to the controller. There is a mode switch on here, which is the one that allows us to isolate the output and put the chair into a safe mode. Down here we have the USB-B socket or plug. I never know which way around they are because the design doesn't really make it that obvious. I think it's a socket, even though it's the one with the pins in it. And then we've got the CAN chips down here. So we've got the controller chip and the transceiver chip. Okay, so then we have a couple of interesting things. One is the power supply setup. well, I suppose that is really the interesting thing at this point. So the problem that we had with the large version of this, with the Arduino Mega sitting on top of it and two joysticks plugged in, etc., was that we made the wheelchair freak out. The controller itself provides 12 volts nominal down to the joystick, because the port that we are connecting into, it only expects there to be a joystick plugged into it and nothing else. So it provides, according to the specs that we could find, I think 100 milliamps is the max that it would supply. And okay, so we've got some interesting results. So Station 240 says some of the TMS320 chips, e.g. the 320F28479D launchpad, 28379D launchpad, and Nick Burton says been using the built-in CAN bus on the ESP32 for a while with no problems. Yeah, that's really interesting. I've been considering switching this over to ESP32 with an external ADC, as Steve suggested earlier, because the ESP32 doesn't really have great ADC support anyway, and so by switching to an ESP32, it would get the built-in CAN support. We would gain Wi-Fi and Bluetooth, which means we could do Bluetooth emulation of a game controller, which would be really cool. Then we wouldn't even need a USB cable, but we would have to add that external ADC, and in that case I'd go for a differential ADC, and then life would be good. So that's quite likely to be in the future for this project. So the big issue is when we powered this with two joysticks plugged in and the Mega, the wheelchair controller would often freak out, and it would detect excessive current consumption on its joystick port, and then it would shut down the output, and then we wouldn't have any power. So what we ended up doing was, through the different versions of this, like on here, there is a little header there for a K78, which way around was this? 7805, which is, you've probably seen the 7805 voltage regulator, a little linear 3-pin. The K7805 is a pin-compatible switch mode replacement, and the idea is that you can just drop it in where you would normally have a 7805 voltage regulator. You put in a K7805, and now all of a sudden you've got much higher efficiency, and it'll take up to 28 volts on the input without overheating, and yeah, it's all good. So I really like the little K780X regulators. I've used them, the 12 volt version, the 5 volt version, and the 3.3 volt version in different projects. It's thicker than a normal 780X voltage regulator, but it doesn't have the heatsink tab on it because it doesn't really radiate much heat. And so you can put down a footprint for a 7805 and then just put a K7805 into its place and you're done, which is pretty cool. So what we did was we had a separate power connection, and we were actually using the DC jack on the Mega, and we were taking 12 volts from an external power supply, feeding it into the Mega, and then taking the V-in pin and then passing that through to this regulator, and then generating power that we were using. So we ended up screwing around with the power setup, and it was basically just a bit of a pain. And what I ended up doing for this version was, I wasn't entirely sure how I wanted to set this up. And so what I did was hedge my bets and put in headers that would allow me to route the power in different directions. So what we've got, if we zoom right in here, is 3 headers. And this particular header, here is the CAN bus header, and I've got a whole bunch of layers turned on that are getting in the way visually here. So now for a CAN, you only need CAN high and CAN low, but what we wanted to be able to do was have interconnects between the devices that would allow us to also pass power down them. So we also have a ground and a nominal 12 volt connection. So the CAN header has the communications and it also can pass power. That means we can plug a couple of different modules together and just power one of them, and then they'll all be powered. So what we also have then is the 12 volts that goes to that header coming to a little jumper. So I've taken that to a 2-pin header, and then I can put a little jumper across that to link the 12 volts to CAN, so that we could isolate that if we wanted to. So what we might want to do is provide power to the different modules individually and not connect power to CAN. So you could take that jumper off and then you're isolated from the power on the CAN bus. And the other thing was, I didn't know if we would need to, on this individual module, take power from the chair or take power from the CAN bus. So what I did here was I put on a 3-way header right here, and it's got ground just as a handy connection, and it's got 12 volts here, which comes in from the which could come in from CAN power, and it also goes to the output of this 12 volt regulator. Oh no, that's the input of the regulator, sorry, which provides power to the rest of the circuit. And then we've got the C12 volts up here is the chair 12 volts. So this is the power that comes from the chair controller. And this gives us a fair bit of flexibility, because what I can do is, if I put a 3-pin header on here, if I want to power this module from the chair's 12 volts, all I have to do is put a jumper across these 2 pins. So I just get a little pin header, put it across there, and now the 12 volts input to this this board is bridged directly to the 12 volts coming from the chair, and that then goes into its onboard 5 volt regulator, which powers everything. And then it's possible to put a second jumper on over on that CAN power location, and then in that situation the 12 volts supply down the CAN connection is also coming from the chair. Or I could leave that jumper off and then not supply that from the chair and supply it from something else. Or if that doesn't work, what I can do is just take an external power input and feed it into these 2 connections where I've got ground and 12 volts, and then I can still optionally feed that down the CAN bus, or I can just leave all of the other jumpers off and pass that 12 volts down to the voltage regulator, and then we are operating in a totally isolated mode where we've got our own external power coming in, going to the local voltage regulator. It's running the local board, but it's not connected to the chair's 12 volts, and it's not connected to the CAN bus 12 volts. So what this little arrangement of headers allows me to do is then have flexibility in terms of where I want to route power from and to. And that seems to have worked fine so far. So I should show you the actual device because we've now assembled 2. Well, we've assembled 1.5. I have the half assembled one here, and so far this is what it looks like. I'll try on this camera for now and then switch to a different camera. So on the input side we've got the connector that goes to the joystick. So the joystick plugs in here and it receives its power from this box, and that is the USB connection going to the 32U4 that is inside it. And now on the other end we've got the pass-through connection. So this connects to the wheelchair. So we just use a little serial extension cable. It's just plug on one end, socket on the other. You connect it from there, goes into the wheelchair controller, and that's the isolation switch. So in the down position, it's sending the signal to the chair. In the up position, the chair is isolated, and then we can send the signal wherever else we want. Now, what I don't have on this right now is the external CAN connections. You can see there are a couple, well, it's actually really hard to see because it's black on black. I'll get the angle right. You can see a couple of holes there. So this end plate I laser cut, and ultimately, that was just like to do a fit test. What I'm going to do is use a CNC machine, and I'm going to do the same thing but out of aluminium. So there will be two connectors on here. Those will be little M8 connectors, so 8mm connectors with a locking thread on them. And those are on order, but I haven't received them yet. So there will be two CAN connectors there, which means that we'll be able to daisy chain through. And then there's another little hole just there, which will be for an LED, which will show power on the CAN bus. So what we can do is unplug the existing joystick connection from the wheelchair, plug it into here, and then we just take another cable from here, plug it back into the chair, and now we have the signal from the joystick broken out to do whatever we want inside here. And we can do HID emulation, and we've already had that working really well. So we can have Nick sitting in his chair using his chair controls and playing a game on the computer, and the computer just thinks you've got a game controller plugged in. And we'll also be able to pass the data out on the CAN bus to whatever other devices we have connected in. And that could be a device that integrates with a FlySky transmitter, or it could be a robot arm or whatever. So what we've done is tested the CAN connection just with jumper wires and things, but I don't have the sockets to be able to make it more permanent just yet. So I'll open this up and show you what's inside, which is pretty much what you've just seen in Eagle anyway, but sometimes it can be cool to see the real thing, not just the design files. Okay, so I designed this PCB very specifically for this case. I basically figured out approximately how much space I needed for all the parts I wanted to put on it. I've got a big box of cases because what I do is order a couple of, I find interesting looking boxes or enclosures and order a few of them just to have them on hand and keep track of where I actually got it from. So I've got all the details of who the supplier is. And what that means is that I can design a project for that specific case, and then if I need more of them, I can just order them. So this case has little mounting rails in it that you can slide a PCB into, and this PCB was designed to fit perfectly into those rails and slide into the box. So the PCB itself is there, it just looks like a real version of what you've seen. And down here you can see, down here you can see the headers for power and CAN and and that sort of thing. I'll chuck this over on the other camera and maybe you'll be able to see it a little bit better. Or maybe not. Now I said that we've assembled 1.5. This is the one that's half assembled, and you can see the CAN bus chips are not fitted on this one. It's got everything else required for supporting it. It's got the crystal for the CAN controller and everything else. And you can see on this one, I've got a jumper on here to bridge down power, the 12 volts from the chair to the 12 volts to the local power. And what we found is that once we switch to using this design and with just a single external joystick with all of this integrated, so we're not running an Arduino Mega anymore, we've just got the 32U4. This actually runs fine from the chair. So what I found is that by putting the jumper in place across the across those power pins to bridge chair 12 volts to system 12 volts. It doesn't draw more current than the chair is happy with, and everything works nicely. So what we can do now is mount this permanently on the chair, connected in series with the control system, and then we can use this to send that to other places. Oh, okay, I need a pause. My throat's getting sore already. Nearly 2 hours of talking, more than 2 hours of talking, which is uncharacteristic for me. So where we were going with this next is that I need to make up a little PCB that will fit onto the back of the connectors we're using for the CAN link, and I'll show you that in Eagle. So this little header down here, which is where the CAN connection comes in, is just a 0.1 inch pitch header. There's nothing special about that. And what I've been able to do is mount the most of the connections on the PCB itself, so they're quite robust. I've got the DV9 connector on one end for joystick, connector on the other for the pass-through to the chair, etc. So this PCB is mostly self-contained. Everything is on that you need, except the CAN connections, and that's just because of mechanical limitations. I couldn't fit any more on the end here, basically, so what I have to do is mount them up higher. If I slide this back into the case, you can see that there is a fair bit of vertical space up here. So the PCB is in the bottom of the case, and then half this box is actually empty. If this PCB was all we had, we could do with this case being half the height, which would be really small. But you're looking all the way through the box there to the holes, and these holes here are where the CAN connectors are going to mount. So they need to have flying leads that go from them down onto the main PCB. And one thing that I hate is making up wiring harnesses. I have spent way too much time getting little bits of wire and stripping them and soldering the ends and things. It drives me nuts. So what I've done is, what we can do is put the sockets, the little panel mount sockets in here, solder cables onto the back of them, and then run them down to the header. But I didn't want to do that. I wanted to make it neater. So I've designed another board, which will be like a tiny little add-on board. And if I go back to my project here, so I've got the Chair Breakout Mini, and I've got the Chair Breakout Mini Con. So I'll open that up, and this is an absolutely trivial little board that is going to fit onto the back of the connectors. So my plan with this is that what I will do is on this faceplate where the holes are, I'll put the connectors through the faceplate, screw it all up so it's nice and tight, and then this PCB that you can see on the screen, which I haven't actually had fabricated yet, and I haven't had it fabricated because I haven't yet confirmed the dimensions of the pins on the back of the connector, will then just slide onto the back of the connectors, and then I'll solder them in place. And what that will do is include a little jumper for a termination resistor, because on CAN bus you can, it's typical to have a 120 ohm termination resistor at each end of the chain. So, and you don't necessarily know where in the chain this device is going to be. Maybe this device will need a termination resistor enabled, maybe it won't. So what I did was, on the daughter board where the connectors are for the CAN, I've included a 120 ohm resistor, which is this one right here, and it is bridged across. So we've got CAN high on one side, and it goes through the resistor to this this pin header, and then to CAN low. So if you put a jumper across this little termination header right here, what it will do is effectively put that 120 ohm resistor across the CAN bus as a termination. But you can just take, the idea is you can just take the little jumper off and then termination is disabled. And then we've got a power LED over here, which is just on this breakout. I've just powered it off the CAN power, and I just stuck a cap on there for the hell of it. So what we've got is a header down here, which actually matches the orientation of the header on the main PCB. So the main PCB has, it's the yellow header just here, and that four-way header exactly matches. And at the moment I'm holding it at right angles, but the way it would actually be is, if you look at the PCB that I've got up on the screen there, in Eagle, that four-way connector matches this four-way connector here, so that a little cable can go from that connector up, bend 90 degrees, and plug into the back of the other board. So I'll just make up a cable that's long enough that it's got some slack and I can slide the PCB out. But it means that what I'll be able to do is have all of the connectors in the case here, with the PCB behind them, the power LED, and a little cable that then just loops down onto here, and it gives the CAN connections like a really convenient way to link to the main board. So all I need then is a little four-way 0.1 inch socket-to-socket cable. I don't need to do hand soldering onto the back of each of the connections on the sockets and then make up a loom, and it's horrible. Yeah, Station 240 said, so you're up to CH. Yes, I'm up to C. Jason Perry says, like the t-shirt. Ah, someone noticed. I ordered this because I wanted to see what it would look like. I just wanted to do like a quality check. It's kind of cool. So, yeah. Oh, and Toby. Hey, Toby. Good to see you on the chat. Says that a lot of line work in Australia uses piercing connectors because stripping cables every day ain't so fun. Yeah, that's absolutely right. Piercing connectors are connectors that just have a little blade or a pin, and when it's clamped around the wire, it penetrates the insulation and makes a connection. And it means you can just put the connector on, clamp it with a tool, and you don't have to strip the wire back, etc. And Station 240 said, yeah, the standard connector for CAN is DB9, which is totally impractical for things like cars, so having the connector off the board gives more options. Yes. So, trying to figure out what connector to use is something that I actually spent a couple of weeks trying to figure out. And I know what connector I want to use, and I can't buy them. And that is the mini, it's the M8 B-coded 5-pin connector. Now the reason for that is that there are some de facto standards around connectors for CAN. And I'm going to pull something up on the screen. Hopefully you'll be able to see it. Over here. I might have to zoom in, I don't know, but I was looking around at places that CAN is used. So CAN is also used in drones a bit. Not really the really cheap consumer level drones. It's used in like mid-range and high-end stuff. So once you get beyond the sort of $50 drone that you can go and buy at the supermarket, and you get up more into the multi-$1,000 sort of systems, particularly once they are specifically designed for operation outside of line of sight where safety is critical, what they often have is multiple CAN buses for redundancy. So you might have a drone control system which has a flight controller. There might be multiple flight controllers for redundancy. There might be multiple GPS modules, which are also talking on CAN, and multiple sensor sets. So it is actually quite common to use CAN to communicate between the different parts of a large UAV. And UAV CAN is a standard that defines partly the electrical connection, so how you connect things together, and also the communications protocol. Because CAN is a serial communications method, but it doesn't actually tell you what to say. Like you can just like any regular serial port. Like if you have a serial connection between two devices, you can send whatever information you like across them. Now, CAN has at the lowest level specifications for how things like packets are constructed and how the low-level communication happens, but it doesn't dictate what information you send. So you can just make up your own communications protocol. You can totally invent something. But in order to have interoperability, you need some kind of a standard way of devices talking to each other. So UAV CAN is an initiative to define a standard for that in the context of UAVs. So this is just one of the things that I came across when I was looking into CAN and considering how we should go about this. And one of the things I had in mind is if there is already work out there to do CAN, to implement CAN in different useful things like flight controllers and sensors and GPS modules, if we can make our system compatible with those existing things, then we can potentially take advantage of them. Say there's a GPS module that has CAN support already, we can just take that GPS module, plug it into our system, and if we can talk to it over CAN, then we can get the benefit of it. And that goes for other things as well, like actuators and other types of sensors. So as we're extending the chair control system, there are all sorts of things we might want to integrate. Like we might want to add a collision avoidance would be cool. One of the problems, of course, is that when you're driving a 200 plus kilo wheelchair and you smack into something, it can really damage it. Like not necessarily the chair so much, it's going to damage whatever you hit. So being able to do things like add LiDAR or ultrasonic range finders or whatever to do collision avoidance, basically just prevent you running into things, particularly at the back of the chair where you can't see. So one of the common problems is reversing the chair and trying to turn, like turning out of a room to align with a passageway, and there might be something else back behind you and the chair swings around and just whatever it is goes flying. So if you don't have to invent everything yourself, it's good. Basically, a lot of people fall for the not invented here syndrome and they want to build everything themselves. But if there's already all of this work that's gone into making something that you can then take advantage of, that's fantastic. So what I wanted to do was try to find ways to make what we are doing compatible with other initiatives, not just start a whole new thing and invent our own stuff. So this comes back to the connectors problem. And on this UAV CAN page, so we've got a specification for UAV CAN itself, and it talks about a whole lot of things about the payload structure and that sort of thing. But there is a section called Hardware Design Recommendations. And if we go into this, we see connector options. So it's got some options in here. There is the obvious one, the D sub connector, and this is what who was it just a moment ago was saying that this was the standard. Sorry, someone there was saying yes, the D9 connector is the standard. So this is the most common one that you see, but it's physically very large. And the other issue is confusion. Because the wheelchair control system is already using these connectors for the joystick and connections to the controller, if we had a box which had two of these on it, and one of them was for the joystick and one was for CAN, you can bet anything you like that someone somewhere is going to plug a cable into the wrong port. So I did not want to have the same port used for two different purposes on our device. And so basically that was ruled out. No chance of using that for that reason alone, quite apart from the fact that it's physically very big and annoying. So on the UAV CAN, they also have a JST GH4 circuit, which is one of those tiny little, I can't remember the pitch, I think it's like 1.25 millimeter or 1.5 millimeter pitch connectors. That's fine for interboard connections, like say you've got, or even on a drone, say you were building a small drone and you had a flight controller and then you had a couple of other devices on CAN. You could use these JST GH connectors, which are tiny, with very small cables to be able to link them together because they're really light, and in that sort of situation they're fine. You don't need protection from the elements because you are connecting on an exposed board anyway, or it's connecting inside like an enclosure of some kind. So it's not, things like environmental protection is not such an issue. But a JST GH connector is totally impractical as an external connector to mount on something like this and then have cables that plug into it, because they're small and delicate and someone's going to break one. Same thing I was talking about before with the USB connector. I went for that big horrible USB-B so that someone who is not in any way familiar with this device or necessarily with electronics can just grab the connector, shove it in. I wanted something that was reasonably robust in the same way. So the third option that they have here on UAV CAN is M8, which is the 5-circuit B-coded version of an M8 connector. So an M8 connector gets its name because it is an 8mm metric, hence M8, locking connector. And they come in a number of different circuits. You can get them in 2, 3, 4, 5, 6, 7, 8 circuit. And they look kind of like a mini DIN connector, but with a locking screw thread on them. And the standard that they have here at UAV CAN is they say to use an M8 5-circuit B-coded. The B-coded just refers to the way the key works, so that you can only insert it one way. And 5-circuit means it's just got 5 pins or 5 sockets. So when I saw this page, I thought, hey, solution, that's great. I'll just get some M8 5-circuit B-coded connectors and we're done. And it turns out that they are pretty much unobtainium, and I don't actually know why they picked these as the connectors, because they don't even need the 5 circuits. So if we scroll down here to where is it? This one. Yeah. This is their specification for the M8 connector. So we've got 5 circuits, we've got bus power supply, 24 volts nominal. That's okay, we can live with that. The wheelchairs actually operate at 24 volts. So the battery pack that runs everything is 24 volts. We can get 24 volts out of the chair, no problem at all. 12 volts is actually like a down-regulated thing that is supplied by the chair controller. So then there's CAN shield, which is optional, CAN high, CAN low, which are the twisted pair that we're talking about, and ground. So in our case, we don't really care about the shield because the environment in which we're working is not extreme. So, and I would have thought that in the case of UAV, because it's a physically fairly small device, it would probably be okay with that shield as well. Maybe they needed the shield because they were running big electric motors and it was generating electrical noise. I don't really know. But in any case, what they've done is they've specified a 5-pin connector for the CAN bus connector. And you just can't get them. So what I was wanting was something more like this. So you can see here, this is the pin out. In fact, I'll I'll zoom in because on this live stream you probably can't read anything that I'm putting up here. So on the JST GH connector, they use 4 circuits, which is ground, CAN high, CAN low, and then bus power, which is exactly what I want. And 4 circuits seems fine. I don't really care about the shield. And when you're doing short connections, that's fine. So what I started doing was looking around on AliExpress and all of the usual sorts of suppliers for M8 5-pin connectors, and they are impossible to find. You can get them from the usual suppliers like DigiKey, the expensive ones, but they're like $26 per connector, and I'm not paying $26 for one connector. So let's see, M8 connector, I'll just search for that. This is exactly what you find when you start looking for M8 connectors. You'll find that the 3-pin and the 4-pin connectors are everywhere. They're really common, really cheap, really easy to get. 5-pin connectors, you just can't find them. So if we have a look at this, this little ad, so these are the connectors. Hopefully you can see this on the zoomed in view. And these are panel mount connectors. You can see there is a 3-pin on the left and a 4-pin on the right. They're physically fairly small, so 8mm diameter, as I said, on the threaded portion, and they've got locking thread on them, so the plug in the socket, push together, and then you twist it and it locks in place. They are very weatherproof, so you could have this on a chair that is out in the rain and it wouldn't really be a problem. They're easy to get the alignment correct. Without really even looking at it, you can physically just jam them together and twist it, and at the correct point they will just pop into place. So these are perfect, and as you can see, they are $1.77 to $2.96 a piece, depending on what type you want. So let's say 4-pin, and in this case it's $3.21 postage to Australia, but we'll say mail insert, so $6.17 including postage for one piece. But that's not the cheapest. That was literally the first ad that came up on AliExpress when I searched for M8 connector. You can get them cheaper than that. So you shouldn't need to pay more than about $2 a connector for this sort of thing. But if I go for the M8 5-pin, I'm paying $26 a connector. So what I've done is I've ordered a whole bunch of the 4-pin M8 connectors in both plug and socket variants. I've also ordered cables. The other nice thing about this is that I think that the reason these connectors are so easy to get from AliExpress is that they are used by Chinese manufacturers for sensor connections of some kind. There's I don't even know what the application is, but there's some, if you do a search for these ads, you'll often find them saying that it's a sensor connect. Well, this one, it actually says sensor connector, flange socket M8, right there. And then you'll find things like sensor cable, and it will be an M8 plug or a socket on one end and then flying leads on the other. And you can get like a prefabricated cable with a connector on the end, and it's all PVC molded and sealed, so weatherproof for $2.50. And so what I've done is I've ordered a bunch of these in different types and cables, and they haven't arrived yet, but that's what's going to go on there. And even though it doesn't actually match anything else, I figured that what this allows is a robust and small connector that that Nick and I can use on our project to connect all of our stuff together. And if we have a situation where we want to plug into something totally different, we can make up an adapter cable or something. We can deal with that when it comes to it. Now and the thing is that that is almost certainly going to be necessary anyway, because if we're wanting to integrate with something like the wheelchair control system, they use CAN, but the connectors they use are insane. Let's see what we can find for, let's see, what's the controller called? Wheelchair CAN bus connector. I'll just search for that for now. And I'll just see if there is an example of it. I can't see one there. But the in order to, I think, make things hard for people, the manufacturers of the wheelchairs do not use any standard sort of connector. In fact, I think the connector that is used on Nick and Chris's chairs, which is one of the most popular chair models at the moment, is custom made. Like, the manufacturer has actually designed their own connector. They haven't even used an off-the-shelf connector. They've designed this really weird connector which has got 4 big plastic fingers on it, and of course you can't get them anywhere else. So if you want to connect into the CAN on the wheelchair, you need to splice into the wire, or what's typically done is you buy the specific cable from the manufacturer, because they make different cables for connecting up chairs that in different ways, because each chair needs to be customized, and the integrators who set the chairs up need to be able to buy cables for linking all the different modules and things together to suit the user. So what you do is you just buy the original cable and then you cut it in half, and then you've got yourself a cable that you can connect, you can plug into the CAN bus on the chair. So the thing is that it's annoying that I can't use a connector that is standard and the same as everybody else. But to some extent, it doesn't matter that much, because we're going to have to make up a custom adapter anyway if we want to integrate with the chair. And if we want to integrate with other things like UAV-oriented hardware, we're probably going to make up cables for that purpose. So I really wish that I could have used an M8 5-pin connector just to be, in keeping with that UAV CAN design specification. But I just haven't been able to source them. So that's my long-winded explanation about the connectors. And I think what I'll do is, because this has been such an epic project, an epic explanation, and I'm heading now towards 2 hours and 40 minutes, I'm not going to go on to the next project. It's just too much. I'm losing my voice. Instead, if you've got any questions, feel free to ask them now. Otherwise, I'm going to wrap this up in a second and go and get myself a drink and have a rest. Figure out what else I'm going to do. Actually, I know what I'm going to do after this. So, questions please. Say something. Okay, so questions. David said, do you have any IoT projects, especially any that use cloud-based AI? I have many, many IoT projects, but I don't have any that use cloud-based AI. And there's a project that I'm working on at the moment. In fact, one of the videos I'm working on for Superhouse is a little sneak preview. This device here, which, where is it? It's got an ESP8266 inside it, temperature and humidity and barometer and stuff. So I'm using this as a project to make a video explaining the process of coming up with the concept for a design, and then taking that through the sequence of prototyping and design validation, and then designing a custom PCB, and then having that PCB fabricated, and then assembling and firmware, etc. So for this project, it shows how to do the Wi-Fi provisioning, and then MQTT reporting, and then taking the data from MQTT and storing it in a database, like a time series database, and then generating charts from it, all sorts of stuff. So in fact, 2 of my upcoming videos, and it'll be a 2-part series, is about designing and building your own IoT devices. But it doesn't have any AI component, sorry. Okay, so Steve suggested I would beef up the trace sizes on the CAN board to make them a bit more tolerant of real world issues. Yes. Yeah, that's a good suggestion. So the trace sizes on this, what are they? They're moderately small at the moment. One of the things about it is that they are is that it's all inside a metal box, which is nice. So for a project like this, come on, won't let me select. There is a weird bug in Eagle that brings up the properties dialog when you don't want it. Okay, try that. Alright, so the trace width is 0.3048 millimeters, and if you are thinking in inches, I can't remember what that is, but let's find out. Inches. Switch my grid to inches, and it is 0.012 of an inch. So it's a moderately thick track anyway. For a signal track, it's kind of thick, and this whole thing is inside this metal box, so it's going to have nice shielding. It's not exposed in a plastic box, at least. But yeah, you're right, Steve. What I should do is just crank up the size of those tracks, make them a bit more robust. There's no harm in doing that, and there's plenty of room on this board. So, as I said, I haven't sent this off for fabrication yet. Hang on, I got the wrong view, so you can't even see what I'm looking at. What I was looking at was this board and these tracks. So, for example, CAN high, which is linking these two connectors together. That is a 0.012 inch track, or a 0.012, which is a 0.3048 or whatever millimeter track. So a lot of signal tracks on PCBs are 0.008 of an inch. So this is 50% thicker than that. But yeah, as you can see, there's heaps of space on this board. It's not like there's any problem with room. So what I can do is go to, what do I make it? 0.012, I can make it. Let's just try making it 0.2. Oh, come on. Why can't I change that? Side? No, I wanted width. That's right. I was changing the wrong thing. We'll make it 0.024, so make it like massive fat tracks. I could do this without any hassle at all, and everything would still fit. So, you know, no reason not to do it if you can. So I'll probably beef up that board. Those are like insano sized tracks. And John asked, have you open sourced the PCB business card you showed in the last stream? That's a good question. I actually honestly can't remember. So let's find out. B-card light. So it seems to have a remote. SuperHouse B-card light. Okay, it does seem to have a URL for a remote repo. So let's have a look. Got GitHub, SuperHouse, B-card light. That should find it. I hope. Yes, it does. There we go. So the short answer is yes, I think. Is it public? Yeah, it looks like the repo is public. So what I'll do is I'll drop that URL into the chat. So if you're interested, you can go and check that out. The artwork on that is rubbish. It's really crappy looking, and I'm kind of ashamed of it, but oh well, someone else can do something that looks neater. Yeah, yes, John Raymond, Unexpected Maker, just said, remember to change the name on it to yours. So then, what else? There was another question. So Steve Cody asked, the CAN transceiver offers 1000 volts isolation. There is no harm in making even signal tracks match that standard. Yep, that's cool. That's a good point. So the CAN bus itself, the physical connectors, like the cables that you pass this over, because it's designed to go in very electrically noisy environments, the specifications are really oriented around those industrial sort of uses. And so if you can get that level of isolation, which means you need tracks that are thick enough for the current that you want to carry, and also have enough separation to provide the isolation. Now, one thing that you might have seen on some PCBs is that, particularly, in fact, if you look at the PCB of a Sonoff, in fact, I think I've got one here. Right here, you will see that they put a slot in the PCB to get as much isolation as possible. And so this is what is this one? It's a Sonoff Basic. Yes, it's a Sonoff Basic. So you can see right through the PCB. It's got these slots in it, and that is because there is neutral. In fact, if we look at the back of the PCB, you can see the big silver thing where they've padded it up with solder. The neutral connection goes up the top, runs along the PCB and down, and then the active comes along, it's here and up and then along there, through the relay, and then down to the other side. But they've actually cut slots or milled slots into the PCB in order to provide a higher level of electrical isolation. And that is a way of making sure you don't get any kind of flashover between the two lines. So in the case of a Sonoff like this, typically you would have 230, 240 volts differential across those. But as Steve points out, the CAN specification, or the CAN transceivers, are designed to give you 1000 volts of isolation. So there's no harm in meeting that as well, if you can. So if your device or your design constraints allow you to do it, then you might as well do it. So yeah, okay. I think I'm pretty much out of energy. I'm gonna crash. So thank you very much for coming along. Oh no, one thing that I should do before I go away, I'm just going to look something up on here, because what I want to do is give a shout out to another, to a worthy maker. Let's see. Someone on YouTube and a channel that you really should be should be following. Let's see, who will I give you some information about? On the last stream, I did a shout out to Unexpected Maker, which is Sion, who is right here in the chat. And this time I'm going to give a shout out to Becky Stern. So Becky has a really cool YouTube channel. She does lots of interesting projects and definitely worth checking out. So if you're interested in making and creating electronics and doing fun things, please go along and check out Becky's channel, subscribe to that, and I'll give you a few other URLs for her as well. So just beckystern.com, and you can also follow her on Twitter, and I'll chuck that URL in. And please also support her on Patreon, because creating YouTube videos is a really big commitment. A lot of time goes into it. It's not just a matter of sitting down for half an hour in front of the camera recording a video and then half an hour is required to produce half an hour of content. It can be weeks of work to design and build projects and prepare everything and then film it and then edit it. So the end result of what you see on YouTube of the work that someone's put into creating a project and documenting it on YouTube is a tremendous amount of work. So if it's within your means, please go along to Patreon and support Becky. So thank you very much for coming along to this stream, and it's quite interesting, and I really appreciate the some of the input that I get as well. So I like interacting in this way, not just working on a video. I mean, I like making videos as well, where I work on them, produce them, edit them, and then upload them. But that's largely a one-way thing. I really like having people on chat like this and being able to talk through things and get feedback and suggestions, and like suggestions for MCUs with built-in CAN that I should be looking at. All sorts of useful stuff. I really benefit from the interaction that I have with all of you. So I'm going to go. Thank you. I hope you have a fantastic Sunday. May still be Saturday night for some of you, but it's nearly lunchtime Sunday for me. And I will see you soon, either in a video or on a live stream. See ya.